The distance measured by EDM systems is invariably the slope distance between the instrument and the reflector. If the horizontal distance is required, then corrections are necessary. For normal survey work, there are three corrections to be considered: an atmospheric correction, a prism constant correction, and a slope correction. For distances which are to be used on the Ordnance Survey National Grid system, a mean sea level correction is also necessary. Consider the measurement of a line AB. A combined EDM theodolite system is carefully set up over point A, and a reflector is set up over point B. The sights on the reflector are used to align it with the EDM system. Parallax is removed, and the center of the reflector is sighted. The EDM unit is turned on, and it carries out a self-check to ensure that it is functioning correctly and that the battery is sufficiently charged. If this is okay, it displays various parameters which were set into it last time it was used: a temperature of 20 degrees C, an atmospheric pressure of 740 millimeters of mercury, and a prism constant of 0 millimeters. It then allows you to change these if necessary. The first step is to apply an atmospheric correction. So, the prevailing air temperature and atmospheric pressure are measured and input. In this case, a temperature of 15 degrees C and an atmospheric pressure of 760 millimeters of mercury. The second step is to input the correct prism constant, which for this prism is minus 30 millimeters. Every prism has a constant which must be set into the EDM unit to allow for the fact that the point on the reflector to which the distance is measured is not exactly over the ground point. The operator activates the EDM transmitter, which sends the wave to the reflector, where some of it is returned to the instrument. The magnitude of the return signal is indicated, and when this is sufficient for a measurement to be taken, a further key is pressed to activate the measuring process. After a few seconds, the slope distance is displayed and automatically updated every 5 seconds. In this case, the distance is 417.019 meters, and it has been corrected automatically to allow for the temperature, pressure, and prism constant values which were input earlier. However, this represents the sloping distance between A and B, and a slope correction must be applied to this to give the horizontal distance. The best way to do this is to use the theodolite to measure the vertical angle to the center of the reflector. So the vertical circle is read and input 092 degrees, 40 minutes, 42 seconds, and an inbuilt calculator enables the horizontal distance to be obtained at the press of a key as 416.560 meters. In more sophisticated EDM systems, the vertical angle is measured automatically. A further press of the same key gives the vertical component of the sloping distance as 19.498 meters. Finally, before moving on, the height of the reflector above point B and the height of the EDM unit above point A are measured with tapes. These enable height differences and reduced levels to be calculated. An alternative method of mounting the reflector is to fit it to a detail pole. This is ideal for use either in detail surveying to establish the positions and reduced levels of features, or when setting out design points on site. When measuring reduced levels, it is good practice to set the height of the reflector to the same height as the EDM unit so that the two cancel out and the difference in height between the two ground points is given directly by the vertical component. To measure a distance, the detail pole is held at the required point with its reflector tilted towards the instrument, and the measuring procedure is carried out as before. Now let's look at an example in which we wish to obtain the horizontal distance d between 2 points A and B. We set up an EDM theodolite system at A and a reflector at B, and we measure the slope length L as 879.922 meters. We then need to measure the vertical angle, because d equals L cos theta. For accuracy, theta should be measured on both faces of the theodolite and the mean value used. So in this case, if the mean value of theta is 0 degrees, 46 minutes, 27 seconds, then the horizontal distance is given by 879.922 multiplied by cos 0 degrees, 46 minutes, 27 seconds, which equals 879.84 meters to the nearest 10 millimeters, which is the typical accuracy of infrared EDM instruments. EDM also enables reduced levels to be calculated. If the height of the instrument, HI, and the height of the reflector, HR, are known, the reduced level of B, RLB, can be obtained from the reduced level of A, RLA, using RLB equals RLA plus the height of the instrument plus the vertical component V minus the height of the reflector. The vertical component V is given by L sine theta, which in this case equals 11.89 meters, again to the nearest 10 millimeters. V is positive for an angle of elevation and negative for an angle of depression. So, if the EDM unit is 1.57 meters above point A, and the reflector is 1.43 meters above B, and the reduced level of A is 415.17 meters above ordnance datum, then the reduced level of B is equal to 415.17 plus 1.57 plus 11.89 minus 1.43, which equals 427.20 meters above ordnance datum. No allowance has been made for the effects of the curvature of the Earth and the refraction of the infrared wave by the atmosphere. Although it is possible to calculate a correction for curvature and refraction, this is not recommended due to the difficulty in obtaining a reliable value for the coefficient of atmospheric refraction. Instead, the distance should be measured again, but in the opposite direction, as soon as possible after the first measurement, and the mean value used. For most everyday surveying work, horizontal distances and reduced levels can be obtained like this with only the atmospheric, prism, and slope corrections being considered. However, if the distances are to be used in conjunction with the Ordnance Survey National Grid Coordinate System, then they must be reduced to their equivalent lengths at mean sea level, MSL. This mean sea level correction is given by DAB times HM divided by R, where DAB is the horizontal length between A and B, HM is the mean height of the ground at A and B above mean sea level, and R is the radius of the Earth, which is normally taken as 6,375 kilometers. The correction is negative unless a line is below mean sea level. So in this case, since the heights of A and B above ordnance datum are 415.17 meters and 427.20 meters respectively, HM is equal to the mean of these, which is 421.19 meters, and the mean sea level correction is equal to minus 879.84 times 421.19 divided by 6375 divided by 1000, which gives minus 0.06 meters. And if SAB is the equivalent of DAB at mean sea level, SAB is given by DAB minus 0.06 meters, which gives 879.78 meters.